Okay, our topic. Today's topic is now force on current carrying conductor in uniform magnetic field. For example, this is a current carrying conductor. This one we are placing in the magnetic field. Okay, consider a conductor carries I current. It is placed in the magnetic field of induction B. Okay, then in this, for example, I current is flowing. I current flows through this wire, right? Consider a conductor of length L. It carries I current. Okay, then it is placed in the magnetic field. We are going to derive the expression for the force on current carrying wire or conductor in uniform magnetic field. For that, what we have to do here, this is a conductor, right? Here L is the length of the conductor, state conductor, and current flows this side. Okay, then electrons flows opposite the direction of the current goes this side, means electrons flows this side. Electron average velocity is called as V suffix d. This minus indicates electron goes right side. V suffix d means drift velocity. The average velocity acquired by the electrons in electric field is called as drift velocity. Drift velocity is Vd. Here I am going to derive the formula for the force on charge. For that, how we can derive the force? Look at here very carefully. And now force on, first this current carrying wire is placed in the magnetic field of induction B. That means the electrons also in the magnetic field. Then the force on charge. Force on charge or the electron. Okay, in magnetic field, force on one electron we can find out. Force on one electron. Force on one electron we can consider as a force formula already we know, that is the force formula is F is equal to QVB sin theta. From this, the charge Q is E, charge force on one electron charge is E, and velocity of the electron is Vd, average velocity of the electron, V suffix d, into B into sin theta, where theta is the angle between the Vd and B. Okay, and now force on conductor I want to find out. Force on conductor which has capital N electrons. Okay, for example, the conductor has n electrons, then what is the force on that? On one electron this much force will act. Force on conductor is nothing but force on n electrons. Okay, here this conductor has n electrons, then the force on n electrons equal to force on conductor, right? On every electron the force will act. Why? Because you know already that when charge moves in the magnetic field, on that force will act. Here electrons are moving in the magnetic field, that's why force will act. When the force acts on the electrons, automatically the force acts on the conductor. That the force on conductor which has capital N electrons. That is, this is the force on one electron. Force on n electrons is N into EVD B sin theta. But we know one formula, number density. Yes. If small n is number density of electrons, okay, number density of electrons, then what is the number density formula? Number of electrons by volume. Number of electrons by volume. The number of electrons is capital N. Volume we write as volume of the conductor, right? Volume of conductor we write as cross section into length. Area of cross section of the wire we can consider as capital A, and the length of the wire is L. Then the wire is in the shape of cylinder, then we write as N equal to N by L. Okay, then here total number of electrons by volume. From this capital N formula we derive, capital N formula we will get as, from this we derive the capital N formula. What you will get the capital N formula from this? Small n into AL we will get. Small n into AL we will get. Okay, this is equation, for example, this is equation 1 and this is equation 2. Now equation 2 substituted in equation 1. Equation 2 is substituted in equation 1. Let us see what you will get. Okay, we want to derive the formula for the force on conductor. Then for that, the force on conductor is equal to force on conductor, right? And when you substitute the equation 2, this one, in equation 1, then we will get the force on conductor as capital N, we write as small n into AL. Okay, capital N we write as small n into AL into this one is what? Remaining capital N replaced with small n into AL. Remaining is E VD B sin theta. We rearrange this one, right? Okay. Now here we write like this. N E A V D we write at one place. Okay. N E A V D into remaining is we write as L B sin theta. What is this NEAVD? We know already. Force for drift velocity for formula we know, that is I by NAE. Okay, from this I is equal to we write as NAEVD, right? This means this is the current equation, right? This is the current equation. Then we write like this, right? Drift velocity formula we know from this. What is the drift velocity formula? I by NAE. From this, I formula is NAE into VD. And here we substitute this as I LB sin theta. This is the force on current carrying conductor. Simple derivation. Okay, this is the simple derivation. And this is equation 3. What is this I in this? ILB sin theta. This we can write as force on current carrying conductor in vector form we write. Force on current carrying conductor. In vector form we write as F bar is equal to ILB sin theta we write as L bar cross B bar. This is equation 4. The force on current carrying conductor formula is either ILB sin theta or IL bar cross B bar, where L bar is the displacement vector. Displacement vector. Or this is a length vector. Actually L is the length of the conductor. L bar is the displacement vector. It is the effective length. Okay. Its magnitude is equal to the shortest distance between initial and final points of conductor. Okay, and direction is equal to, direction is in the direction of current. Direction is in the direction of current. Okay, right. And what is B in this? B is the magnetic induction, we know already. I is the current. Theta is the angle between the B, L and B. Theta is the angle between the L and B. We have to write all the terms. Okay. I is the current, L is the length, B is the magnetic induction, theta is the angle between the L and B. Here we write one, since why we are writing like this. Here LB sin theta we write as L bar cross B bar. L bar cross B bar. We know already formula. AB sin theta equal to A bar cross B bar. By using that formula we write this one. Okay. Take the screenshot and note it. This is the derivation for the force on current carrying conductor in uniform magnetic field. Its formula is ILB sin theta. Okay, where I is the current, L is the length, B is the magnetic induction, theta is the angle between the L and B. We take that angle between the L and B, or angle between the V and B also we can take. Okay, right. Here we can write the terms also. If you want, you can write here. Okay, take the screenshot and note it. What are the terms here we have? Right, I will write the terms also. B bar is what? B bar is magnetic induction. Theta, angle between L bar and B bar, right? With this topic is completed. Okay, I will continue later. Okay, let us continue. Just now we derived the formula for the force on current carrying conductor. Some points I am going to give related to this note side heading, right? What formula you got the force on current carrying conductor? Right, the force on current carrying conductor is force on current carrying conductor. Force on current carrying conductor. In uniform magnetic field. In uniform magnetic field. What formula you got? We derived just now, right? That the force formula is ILB sin theta, right? In vector form, if you want to write, F bar is equal to, we write as I into L bar cross B bar. This we derived. This is very important formula. Okay. Now this is in vector form and this is magnitude form. What is L in this? L is the length of conductor, but we have to take the effective length of conductor. Effective length of conductor. Effective length of conductor. Okay? Effective length of conductor. What is effective length of conductor? What is effective length of conductor? If the conductor is not in straight line, okay? L is the length of the conductor. But if the conductor is like this, they are semicircle, like this. In this moment length we cannot take the original. We have to take the shortest distance between the initial and final points of conductor. If it is semicircle with r radius, then we take the length of the conductor as 2r, not original length of the wire. Right? There is a difference. Effective length is nothing but it is the shortest distance between initial and final point of conductor. Shortest distance between initial and final points of conductor. Okay, that you have to remember. This is very important point. Shortest distance between initial and final points of conductor we have to take. And now let us see what is theta in this. What is B? B is the magnetic induction, and theta is angle between L and B. Angle between L bar and B bar. Okay, right. Now let us discuss few cases in this. Now first case 1. Okay, first case is that if L bar parallel to B bar, right? L bar parallel to B bar. L is the displacement vector or effective length vector. It is a vector. Length is a vector. What is its direction? Its direction is along the direction of the current. Okay, and its magnitude is equal to shortest distance between the initial and final points. Then theta, what we take? theta we will take as 0, right? Its diagram I will draw it here, look at carefully, and this is a wire, okay, and it is the length of the wire. Length we are taking as a vector, and the magnetic field is right side, the magnetic field is right side, and the length is also right side, the current also flows right side, right? Current also right side. Then at that moment what we have to do, we have to take here L bar parallel to B bar. L bar is along the direction of the current, current is right side, and field also right side, right? L bar and B bar are parallel. This is a current carrying wire, and it carries the current I, and field also right side. Then L bar and B bar are parallel to each other. Then at that moment this we can write theta is 0. Then the force on current carrying conductor, force on conductor, what happens? Force on conductor is ILB sin theta. Theta is 0 at here because LB are parallel to each other. We take the force as 0. No force on the conductor if its length is parallel to field. Okay, what is the length? Length is the effective length we have to take. And now let us go for one more case. That is the case 2 is that if L bar parallel to B bar, okay, if L bar perpendicular to B bar, let us see, effective length is perpendicular to B bar, then here we take the theta as 90 degree. Then what happens to the force on conductor? Then the force on conductor here, like this, the situation will be there. For example, this is a conductor, right? It is in semicircle shape. It carries I current. Now for example, it is placed in the magnetic field. The magnetic field is just like a cross. Magnetic field is cross. Then what we write the force on this conductor? The magnetic field is like this there. What is the force on the conductor AB? Okay, this is the conductor AB, and its radius we can take as, let us consider, this is the radius is smaller. Okay, then the force on conductor is what? What is the force on the conductor? And for example, one more point I will take. This is figure A, let us consider figure A, and one more figure I will give. This is the straight conductor, right? Now its length is L. Okay, and it carries I current, and it is placed in the magnetic field. For example, the magnetic field is like this there. This is the direction of the magnetic field. Okay, magnetic field is like this there. Then LB are perpendicular to each other, right? In this case, this is the figure B. In these two figures, I want the force formula. Okay, force on conductor, right? In above figures, okay, length and field are perpendicular. In figure A and figure B, L perpendicular to B, L bar perpendicular to B bar. That's why theta we will write as 90 degree. How L perpendicular to B bar? What is L here? What is L? L is like this there actually. L is this length. Pi r is the length of this one. Okay, length of this one is pi r, right? Semicircle. It's a semicircle. Pi r length it is. But we don't take that length, original length. We have to take as per length. Length of the conductor is the effective length of the conductor we have to take. That means it is the shortest distance between the initial point and final point. You join the initial and final points like this, we will get the shortest distance as 2r, is it right? And this will become the length of the conductor. The length of the conductor is right side, right? Length is right side. Look at here. Length is right side. Why? Length is a vector, but its direction is in the direction of the current. Current goes from A to B. Then effective length is A to B. Length is 2r we have to take. We should not take this length. Okay? We have to take the effective length. Means it is the shortest distance between the initial and final points. Conductor, if it is not in straight, at that moment, the original length of the conductor is not equal to this effective length of the conductor. Okay, original length here pi r we will get, but the shortest distance between the initial and final points we will get is 2r. That is only effective length. Means here in this case effective length is 2r. The effective current is right side. Okay, then the length we will take like this, A to B. Okay, field is inward, just like this. Length is right, this field is upward in this 90 degree, but length is like this, field is inward, right? Here also perpendicular. Oh, this we will take as not A to B, oh, we take it as X, Y, because B is already magnetic field is there. Okay, and now what do you write the force on conductor? Force on conductor becomes maximum. Why maximum? Force on conductor formula is what? ILB sin theta. ILB sin theta. When theta is maximum, okay, sin theta value maximum, then the force also maximum. Then we write the force, maximum force formula is, right, or the force formula we write as directly, what you will get? ILB sin 90. But here we will get as sin 90 is 1, that we will get as force as ILB, and this is maximum force. This is maximum, right? The maximum force formula is ILB. In some books it may be written as BIL. Okay, this is the two cases, case 1 and case 2. In figure A we write figure A force formula. What we write? In figure A the force formula we write as I into LB, but L we write as 2RB. Okay, and in figure B we write force. Figure B force we write as ILB. ILB. L is the length, B is the magnetic induction. But here the length is not this length. Okay, length we should not take as pi r. Okay, it is a semicircular. Original length is of the wire is pi r, but we should not take the pi r. Effective length of the conductor in formula ILB sin theta is there, but L is the effective length of the conductor. Effective length is from straight line distance from initial point to final point. Okay, we have to take the effective length. That means this length we have to take straight line length. Okay. Initial point this one, final point this one, final point of conductor, initial point of conductor, final point of conductor. Join them with a straight line, this length, just like displacement. 2r is the effective length, L is equal to 2r, right? Okay. Take the screenshot and note every point. I am going to rub it and I will continue. Now I am going to explain the Fleming left hand rule. Look at here, Fleming left hand rule. What is the use of the Fleming left hand rule? Okay, we know that the force acts on the current carrying conductor. To know the direction of the force, right, in which direction the force will act on the conductor, whenever the current carrying conductor is placed in the magnetic field, on that force is acting. To know the direction of the force, we will use the Fleming left hand rule. Okay, then what is this rule? Let us see. Here the Fleming left hand rule is used to know the direction of the force on current carrying conductor. For example, this is a current carrying conductor. It carries I current and its length is L. Okay, now it is placed in the magnetic field. The magnetic field is B. On this some force will act. To know the direction of the force on the current carrying conductor in the magnetic field, we use the Fleming left hand rule. According to this rule, what we have to do? We have to stretch the, look at here, this is thumb, this is forefinger, this is central finger. Stretch the thumb, forefinger, central finger of left hand in such a way that they are mutually perpendicular to each other. These two are perpendicular, these two are perpendicular, and these two also perpendicular. All the three are mutually perpendicular to each other. Then after that, what you have to do, if the forefinger shows the field, magnetic field, forefinger magnetic field, central finger C current, then the thumb shows the direction of the force on current carrying conductor. Forefinger field B and central finger current, then thumb shows the direction of the magnetic field. Look at here, this is the diagram. Okay, forefinger indicates the field and central finger indicates the current and thumb indicates the force. Okay, in the diagram it is little bit different appears, but actually the thumb will shows the direction like this. Okay, you should use the left hand. Now the stretch the forefinger, central finger, thumb of left hand in such a way that they are mutually perpendicular to each other. If the forefinger indicates the direction of the magnetic field, central finger indicates the current, then the thumb shows the direction of the force. Very simple. Forefinger indicates the field, central finger indicates the current, then the thumb indicates the force. This is our Fleming left hand rule. Let us see here how we can apply this Fleming left hand rule to certain situation. Let us see with one example. Okay, now here I gave the one example. Give direction of the force on conductor in below figure. Here what I wrote, forefinger indicates the magnetic field, central finger indicates the direction of the current, R direction of the current, R, this is R. What is R? Direction of the flow of positive charge. Direction of flow of positive charge only direction of the current. And the thumb indicates the direction of force on conductor. Forefinger field, central finger current, thumb force. Give the direction of the force on conductor in below figure. Look at here, this is the figure. In this current carrying conductor is placed in the magnetic field, then it will experiences the force. Now how to tell the direction of the force? To express the direction of the force, you have to use the Fleming left hand rule. First you stretch the fingers like this, okay, habituate. After that you have to, here the direction of the current we know, direction of the magnetic field you know. First you arrange the forefinger to the field, magnetic field, central finger to the current, then automatically the thumb shows the direction of the magnetic field. Okay, here field direction is you know, then forefinger you can keep towards the field, central finger you can keep towards the current, then the thumb itself it will shows the direction of the force on conductor. But while rotating this like this, okay, look at here, yes, you can rotate your wrist like this, but while rotating these fingers always mutually perpendicular to each other. This finger's location you should not change. You should not change like this, like this, like this, like this. You should not rotate the fingers. You can rotate like this. You can rotate like this. But always the fingers are mutually perpendicular to each other. Now here let us see the example very carefully. And look at here. The field is inward. The cross indicates the inward. Okay, this is the forefinger. This side it will be there. If you go like this, if you see like this it is there. But if like this there means forefinger this side, right? But forefinger should be into the board, right? Field is inward. Field is inward. Okay, field inward. Okay, forefinger indicates the field. Field is inward into the board. And now field is inward. What about the current? Current is not downward. Central finger indicates the current, but the current is right side, right, like this. Okay, then the current is left side. Current is left side, and field is inward. Then thumb indicates the force. The force is upward. Then from this we say that the force is upward. Force is upward, like this. Okay, forefinger indicates the field. Field is inward. Center finger indicates the current. Current is left side in this example. Okay, then the force is upward. Okay, automatically it will shows the force is upward. Once again I will repeat how we have to tell. First you have to adjust the forefinger towards the field, that is to inside into the field. Then after that you have to arrange the center finger towards the current. Current is right side. Forefinger indicates the field. Thumb automatically shows the upward. Right? That means the force is in upward direction. Force is in upward direction. Okay, the force direction is completed. Next, let us go for the one example. Okay, for example, this wire is suspended in mid-air in the magnetic field. Then what is the condition for that? Okay, I will rub this side and I will continue. Okay. If the wire is at rest in mid-air. Okay, this is a wire, it carrying the current I, it is in the magnetic field, the magnetic field is inward, this is the magnetic field, the magnetic field is inward. Now at this moment the force will act on the conductor. What is the direction of the force? You know already, the force is upward. Okay, right, the force is upward, but its weight will act in downward direction. The weight will act in downward direction. The weight is mg. If these two are balanced, then this wire is suspended in air. Is it right? Then if the wire is at rest in the mid-air, condition is that upward force must be balanced with the downward force. Okay, like this. For example, this is a current carrying wire. It is suspended in air. It is never fall down. That means on this upward force should be balanced with its weight. Gravity pulls down, but it should not go down. Means some upward force should be balanced with the downward force. The condition is that upward force must be equal to downward force. What is the upward force? Upward force is the force on current carrying conductor. That is ILB sine theta. ILB sine theta. Downward force is mg. But sine theta, theta is what? But the L is perpendicular to B. Is it right? L bar perpendicular to B bar. That's why theta is 90 degree. Look at here. L is like this there. L is like this there. Length is like this there. Right? Field is inward. And length and field are perpendicular. Length will be this one and field will be like this. They are perpendicular to each other. Right? Then we write theta is 90 degree. Then here ILB sine 90 is equal to mg. Then condition finally we will get is ILB is equal to mg. Right? This is the condition. And now one more example I will tell. Give the direction of direction of magnetic field. Direction of force on conductor. Force on conductor in magnetic field. Right? I want the direction of the force. Now the diagram is that this is a current carrying wire. The current flows in upward direction. And now this is placed in the magnetic field. This is the magnetic field. It is placed in the uniform magnetic field. Then what is the direction of the force on this conductor? Right? The field is inward. The forefinger should show the field. Look at here. Here the first of all stretch the forefinger, central finger, thumb perpendicular to each other. Then after that you have to arrange the forefinger in the direction of the field. Field is inward. Cross indicates into the board. Okay. Field is inward. Okay. Forefinger indicates the field inward, but the current is not here. The current is downward, but not downward, upward. Okay, look at here. The field is inward. Field is inward. The current is upward. Then the thumb indicates left side. That means the force on this conductor is left side. Okay. Force acts on conductor in left side, right? Okay. This is how to know the direction of force on current carrying conductor. Let us go for one problem based on this. I will give the question and you solve it and send the solution to me. Look at here, this is our question and it is very important question. Now try for the solution for this. Okay, the question is that a straight wire of mass 200 gram. Okay, right. Solution. What they gave here? Mass they gave 200 gram. You convert this into kgs, 0.2 kg. You have divided with 1000, right? You will get the 0.2 kg. And length they gave was 1.5 meters, length of conductor. Wire mass, wire length they gave. It carries current of 2 amperes. 2 amperes current. It is suspended in the mid-air by uniform horizontal magnetic field. Due to the magnetic field, it is suspended in the mid-air. Then what is the strength of the magnetic field? What is the magnitude of magnetic field? B is what? That is our question. Already I set the condition for the suspension, right? Look at here. This is a current carrying conductor. The field is inward. Then the weight acts in downward direction. Then if the force acts in upward direction, magnetic force, this current carrying conductor is placed in the magnetic field, okay, and due to that some magnetic force acts on this. If that magnetic force, right, if that magnetic force, what is that? ILB sin theta. Theta is 90 here, again L and B. L is like this, B is inward. Then ILB sin 90 you will get. If these two are balances, right, upward force and downward force. Downward force is gravity, weight. Then it will be suspended in the mid-air. Then condition is upward force equal downward force. By using that condition you can find out the B value. It was very easy. And also along with this question you can also solve one more question. That is one of the example in the NCERT book. I will give the number. Okay, look at here. You solve this problem and after that you can write the answer in the comment and also send the solution to me in WhatsApp. And the NCERT example 4.10 also you can complete. This is also very important. Solve in your notes this one. And this is based on the force and current carrying conductor. F is equal to ILV sin theta. Right? Thank you for watching my lectures. Subscribe my channel. Share to your friends.